Well, since in reality most motion is damped by something,
I sincerely hope so.
we should investigate what that equation would be. So, free undamped motion just doesn't occur except in space, although it appears in some applications. A more realistic approach would be considering as a damping force acting on the weight that is proportional to its velocity. So in other words, the faster it goes, the more it's damped, right? Does that make sense? The quicker it goes against the wind, the more a windbreak or the more having a sail would affect your velocity. Anyway, at any given time, you'll see there will be friction with surrounding medium that slows it down. Maybe the system itself has a damping mechanical device. Some devices are like that. Think of the shock absorbers on your car. Those are damping devices. The springs don't continually bounce up and down after you go over a bump, although if they do, then that means you got to replace your shocks. Then the shocks act to dampen the bouncing. So, calling that proportional to the velocity adds to the differential equation, and it becomes, see, the velocity is first derivative of the equation of motion. So, mass times the second derivative equals proportional to the displacement minus b, so another proportion, to the velocity for some positive constant b. And of course we could rewrite that like this, and if we let one more thing, an external force, act on the weight, then it's no longer a homogeneous but a non-homogeneous second order linear differential equation. So the solution to this equation will give the displacement y of t of the weight from its equilibrium position at time t, and the initial conditions y of t0 equals y0 representing the initial position of the weight, and y prime of t0 equals v0 representing its initial velocity.
Oh, darn!
Yeah, so we have it right there. It is. That is our equation.